All right. The only reminder before we start is that today's office hours, as I mentioned last time, were a little bit different. So they're going to be 12 to 1 p.m., 1/2 hour later than normal. All right, so if you're planning to stop by, just keep that in mind. And today I'm pretty much booked solid except for that hour, so I won't have a lot of flexibility, but if you come during 12 to 1, I'll be there and available to talk. All right, so what we're going to do today is we're going to finish chapter 8, which is the chapter on gases, and that will then move us into the very last chapter in this course. So the material that we cover today will not be covered until next week's homework assignment. So there's 2 homework assignments on chapter 8. The one that's due this coming Sunday, it covers up until what we finished last time. It also has a couple of the last topics from chapter 7 still, even though it's called a chapter 8 homework. It includes the stuff about energy and fuels that we talked about at the very end of chapter 7, first half of chapter 8, and then next week's will be pretty much all the stuff that we cover today. So what we're going to talk about today is it's called the kinetic molecular theory. So things are going to get a little bit more conceptual now, at least at the start of this lecture, although there's going to be some calculations and quantitative things we'll do related to this. So this is kind of helpful now to think about back to the very first part of the course. This is obviously a totally different topic, but we're taking the same approach here. So remember in chapter 1, we learned the 3 mass laws: conservation of matter, definite proportion, and multiple proportions. So those 3 mass laws that we learned at the beginning. And then we came up and talked about Dalton's atomic theory, which is a theory to explain the mass laws. So again, that's how science works. You observe things, you formulate a set of behaviors, which are called laws, and then you generate a theory to explain those laws. And now we're doing the exact same thing in chapter 8, but now on the topic of gases. So what we talked about last time was the ideal gas law, which describes the behavior of any ideal gas in terms of its pressure, volume, number of moles, and temperature. So we can now use that gas law to make predictions about how the properties of gases will change under different scenarios. And now what we're going to do today is we're going to describe a theory called kinetic molecular theory, which explains the behavior of gases. So again, that's kind of the 2 parts of any sort of scientific development: a law, which is a description of what happens, and a theory, which is a description of why it happens. And so kinetic molecular theory is going to be the theory that describes the behavior of ideal gases. And it can be broken down into a few different postulates or a few different parts, which we're going to go through now. So again, this is sort of the conceptual basis of how gases behaved. So the first thing in kinetic molecular theory is that the particle volume, so the atoms or molecules that actually make up the gas, is assumed to be 0. Now, right off the bat, this should strike us as an assumption that's not quite correct. We know that atoms have some volume to them, some size to them. And so essentially what that means is that in this kinetic molecular theory, you're treating gas particles as point masses. So they have mass, but they don't have volume. Now, as we know, that's not rigorously true. But again, a lot of theories have assumptions built into them to make them work, and this is one that we're going to use for kinetic molecular theory. So gas molecules, atoms or molecules, whatever's making up that gas, they're assumed to have mass, of course, but they have no volume. All right, now the important one here is number 2. I think this is probably the most important one to realize, which is that the gas particles, atoms or molecules that make up the gas, are in constant random motion. All right, and so that sample of gas that you have is made up of atoms or molecules that are constantly moving around. And so if they're enclosed in some container, be it the walls of the room that you're in, or a fixed container if you're studying it in sort of an experimental setting, those gas particles are going to collide with the walls of the container constantly. And so it's those collisions that cause pressure. So the collisions of the gas particles with the walls of the container result in what we know as pressure. All right, so that's why we have pressure observed whenever we have a sample of gas, because the gas molecules or atoms are moving around really fast, and they strike the wall of the container on a regular basis, and that exerts a pressure. Now, even though we now have said in point number 2 that the gas particles, they exert a force, a pressure on the walls of the container they're in, we assume in the kinetic molecular theory that the particles do not interact with each other. So they behave independently as if they're, again, as if they're the only one present, just like we talked about in the context of the law of partial pressure we talked about last time, Dalton's law. But the particles exert no forces on each other. So they can randomly collide with each other, of course, if they're all moving around like that, but they're not attracted to each other in any way, or they don't repel each other in any way. They just randomly fly around. If they run into each other, they might transfer momentum in that way, but they're not exerting any sort of regular force on each other. They're just, again, zooming around independently. And then another important one, which we're going to talk about in more detail quantitatively in a little bit, is that the average kinetic energy of the gas particles is proportional to the temperature. So kinetic energy is proportional to temperature. We'll define this in more detail later on, but if you've taken your physics course or are in the process of that, you'll know that kinetic energy is 1/2 times mv squared. And of course, the temperature for this to be true has to be in the absolute scale of Kelvin. But what it says is that as you raise the temperature in a sample of gas, the kinetic energy gets higher, meaning that the gas molecules start moving faster and faster. So how fast those gas molecules are moving, we will see, is going to be dependent on the temperature that they're at. All right, and when you raise the temperature, then the gas molecules are going to be moving faster and faster, so they're going to hit the walls of the container more frequently, and they're going to hit the walls with more force. So both of those, as we'll see, are going to affect the pressure. Because if you raise the temperature, you're going to have more frequent collisions with the walls of the containers, and they're going to exert a larger force when they do collide, because they're moving faster. All right, and so these are kind of the 4 things, and really boiling it down to the important thing is that gas molecules or atoms are moving around constantly. They run into each other randomly, and they also run into the walls of the container, which generates pressure. So that's really what kinetic molecular theory is all about. So then let's talk how this relates to the ideal gas law, because we knew from before the relationships between all of these: pressure, volume, number of moles, and temperature, and then we have a theory that kind of explains that. Let's see how they kind of work hand in hand. So the first relationship we talked about was Boyle's law, which is the relationship between pressure and volume. So rearranging the ideal gas equation and putting pressure and volume on 2 opposite sides, pressure is equal to nRT times 1 over volume. So again, pressure and volume are inversely related to each other. And so here's what this diagram here is showing. So what this is sort of illustrating is a simple experiment with gases where you have this top lid here is a movable lid, so it can move up and down as the pressure of the gas changes and so on, or volume can expand and contract. And you can see you have a little weight on top of that that's exerting a downward pressure on the gas. And then what they're showing here is they put a second weight on top of that. So you're basically increasing the pressure, external pressure on that gas, on that sample of gas. So anyway, what we're showing here is that, what happens when the volume is decreased. So when the volume is decreased, we know from kinetic molecular theory that if we're not changing the temperature, we're not going to change how fast the gas molecules are moving. They're going to still be moving the same speed. But if we decrease the volume, they're still going to collide with the walls of the container more frequently. So when we're thinking about these gas laws at a microscopic level, we should think about the 2 things that control what pressure we're exerting. One is how forceful the collisions are with the wall, which is a function of how fast the gas molecules are moving. And the other is how often they hit the wall. The more frequently they hit the wall, the higher pressure they're going to exert. So if we change the volume here at a constant temperature, we're not going to change how fast the gas molecules are moving, because they're still at the same temperature, but we're still going to have more frequent collisions because the volume is smaller, and so the gas molecules are more likely to run into the walls of the container as you shrink the volume. So when you shrink the volume, the collisions become more frequent, And if you have more frequent collisions, they're going to hit the wall more often, and that's going to raise the pressure. So again, those are the two things that can increase the pressure. Either they're striking the walls of the container with more force, meaning they're moving faster, or they're striking the walls of the container more often. And in this case, if you shrink the volume, the frequency of collisions becomes higher, and that's going to raise the pressure. And we know if you shrink the volume, pressure will go up based on Boyle's law or the entire ideal gas law equation. Now let's talk about a relationship between pressure and temperature. So we didn't have a gas law named for this, but we can predict it from the ideal gas equation. So again, we're going to move pressure and temperature onto opposite sides, and so pressure is going to be equal to nR over V times the temperature. So again, we're assuming that the other three things are constant. Well, R is always constant. We're assuming same number of moles, same volume in this case. So we're keeping the volume constant in this case. We're not moving the lid of the container at all. And what we would predict from this equation is that as the temperature goes up, so does the pressure. So let's think about what happens when we increase the temperature. So when we increase the temperature, as we said from the kinetic molecular theory, and we'll talk about in more detail mathematically in a little bit, the particles move faster. And because they're moving faster, that's going to cause two things when you talk about their collisions with the wall of the container. So they're going to hit the container walls with more force because they're moving faster, and they're going to hit the container walls more frequent. Both of those are going to happen because if they're zooming around at a faster speed, they're more likely to hit the wall of the container as well, in addition to hitting it with more force. So the particles move faster and the collisions become more frequent. So both of those are going to happen whenever we raise the temperature. So the collisions with the walls are going to be more frequent and more forceful when the particles are moving faster, and both of those will then contribute to raising the pressure. So when the temperature goes up, the pressure goes up. We would predict that mathematically, and this behavior of gas laws at the of gas particles at the microscopic level helps us understand that. All right, and then let's talk about the other two gas laws. So we had the relationship between volume and temperature, which is Charles's law. This one kind of follows the same the same logic we just talked about for pressure and temperature. So this time we're just going to have volume and temperature on opposite sides. And again, Charles's law tells us that they're going to be directly related to each other. If one goes up, the other one should go up as well. They're both directly proportional. And so what we're doing here is we're keeping pressure constant. So we're not changing the amount of force that's pushing down on the gas. We're keeping a constant pressure in the gas, but we're allowing the volume to change under this situation here. So if we increase the temperature, again, what we just said is that when you increase the temperature, the collisions of the gas molecules with the container are more frequent and more forceful. So if you're allowing the volume of the container to expand and contract, as those gas molecules are hitting this top surface, this top lid here with more force, and they're hitting it more often, they're going to push that lid up, and that's going to increase the volume. So the volume increases as a result. So pretty much the same logic as the last one, but now we're just allowing the volume to increase, and when you have more collisions with the container, the volume will increase because you're pushing up on that container, expanding its volume if it's allowed to expand, if it's not a fixed volume. And then finally, volume and moles, which is Avogadro's law. Those two are also directly related to each other, as we talked about last time. So rearranging the ideal gas equation, we find volume and number of moles are directly related to each other. So if we pump more gas into the container, so what we're showing here is we're keeping the pressure and the temperature constant, but we're pumping more gas into the container. We're adding more moles of gas to that sample. So when we increase the number of moles, we have more gas particles present. Again, atoms or molecules, depending on what the gas is made up of. And when you do that, you're going to have more frequent collisions. We're not increasing the temperature in this case, so the speed at which, the average speed at which the gas molecules is moving stays the same. So we're not going to have more forceful collisions, but we will still have more frequent collisions because there's more molecules present that are moving around, and so then you're going to have collisions with that wall happening at a more frequent rate. So whenever you have more collisions with the wall, again, that's one thing that can cause the pressure to increase. And that's going to increase the volume as well, because again, we're allowing the volume to expand here. So if you're if you're pushing on that lid with more frequent collisions, it's going to push that up and you're going to increase the volume as a result. All right, so all of these microscopic level arguments hopefully help us understand why the ideal gas law is the way it is and why the relationships between pressure, volume, number of moles, and temperature all sort of follow the way they do. So it's really only two things to think about when you're changing something about a sample of gas. Are you increasing how fast the molecules are moving, which would increase both the force and the frequency of the collisions, or are you just increasing the frequency of the collisions if the temperature is the same? But again, if you change the volume or add more gas, you can change how often those gas molecules collide with the walls of the container. So those are really the two things that influence pressure, and hopefully that makes sense now why we have these relationships that involve all these different parameters. So any questions on that conceptual stuff before we move into a little bit more quantitative description of this? All right, so what we're going to talk about now is sort of how fast are gas molecules moving, or at least in a relative sense. If we compare two different samples of gas, how fast on average are they moving? Now, the first thing to recognize is that when you have a sample of gas at a certain temperature, and we said that there's a relationship between temperature and how fast they're moving. If you increase the temperature, on average they move faster, but not every single atom or molecule in that sample is going to be moving with the exact same speed. It's not like there's one speed that they're all moving. There's always a distribution of speeds. So that's the important thing to realize conceptually first, is that when you have a sample of gas, the atoms or the molecules that make up that gas will possess a distribution of molecular speeds, not one single value, but a range of values. And if any of you have taken a statistics course, this sort of distribution and some of the things we're talking about will make a lot more sense, but you don't need to have statistics to understand it at the level that we're talking about it. But it's all about a distribution of speeds that are present. So let's talk about then how that looks for different gases under different situations. So the first plot I'm going to draw, we're going to compare the same gas, so just one type of gas, let's just say helium for argument's sake, and we're going to change the temperature of that gas and see what happens to the molecular speeds. So what we're going to be plotting here on the x-axis is going to be the different molecular speeds that it can have from low to high, going left to right. And then the y-axis is fraction of molecules. What percentage or what fraction of the molecules have that specific molecular speed? Now we're going to do this for now qualitatively. We're not going to talk about the mathematical aspects just yet, but qualitatively, let's start with a gas that's at low temperature. And so what this would look like is something like this. You're going to have a distribution of speeds. So it's going to have some speed that's the most probable, but it's going to really be distributed over a wide range of possible values. So it would be something like this, kind of like it's not exactly a bell curve, but kind of like a bell curve, where there's a distribution of possible speeds that molecule can have. Now, one thing to recognize, as we talked about in the kinetic molecular theory, is that the temperature is proportional to the average kinetic energy. So in statistics, sometimes you'll see a bar above something that means average. So the temperature is proportional to average kinetic energy, and this is equal to 1/2 times the mass times the average speed squared. Okay? So this mathematical relationship we're going to talk about in more detail, but that's kind of at the heart of all of this. So as you increase the temperature, you're going to increase the average kinetic energy, and you're going to increase the average velocity. Yes?
So V stands for velocity. Is that velocity squared?
Yeah, so V is velocity, how fast the molecules are moving.
And what's M for?
M is mass.
Oh.
So 1/2 mv squared is the equation for kinetic energy. Here we're talking about one sample, one type of gas, let's just say helium, so the mass will be the same for all these different ones. We're just going to talk about how the changing temperature increases the average speed and the distribution of speeds that we have. All right, and so what we're going to do now is let's go to an intermediate temperature. Let's do that in green. All right, so if we go to medium temperature, so we're going to raise the temperature a little bit. Again, this is all qualitative, low, medium, high. We're not talking about specific numbers here. So what's going to happen is what this equation tells us is that the average speed will increase as we raise the temperature. So the peak is going to shift to the right because it's going to be a higher average speed, and also we'll get a wider distribution. So as we increase the temperature, we also get a wider distribution of speeds. So this one will look something like this. It's going to be overall shifted to the right, but it's going to be a little bit broader distribution as well. All right? So it's a broader distribution. The integration under these curves should be the same. I'm probably not drawing it perfectly, of course, but ideally it's the same number of molecules, so the integration under this is the same. But it's whenever you raise the temperature, you get a broader distribution, and we see that the average sort of shifts to higher values. So our average speed can be sort of represented as the peak here. That's not exactly correct, but for our purposes it's fine. And then you can see this peak shifts to higher and higher velocity as we raise the temperature. So the last one I'll draw is an even higher temperature in red. And when that happens, of course, we make an even broader distribution with a further shift to the right. All right, so every time we raise the temperature, we broaden the distribution and we shift the average further and further to higher values. So we're making that, on average, the molecules will move faster as we raise the temperature. So that's kind of qualitatively what these distributions will look like. All right, and then the other thing, and so this velocity here is the most probable velocity, which is sort of a proxy for the average. If you assume a perfect bell curve, it would be. All right, and the next thing we're going to see is what happens if we look at different gases all at the same temperature. So now what we're going to compare are 3 different gases, but all of them at the same temperature. So again, we're going to look back at this equation here to see how their distributions are going to change as a function of different gases. So let's first start with O2. And let's just assume that it has this particular distribution at a certain temperature. All right, so let's say that's oxygen. I'm just going to randomly draw that one in first. Now let's go to a lighter gas, helium. Okay, so the molar mass of oxygen is, so we're going to have 1 mole of each gas, assume the same amount of each gas. And now let's go to helium, which has a smaller molar mass than oxygen. So oxygen is 32, helium is 4. So we're going to a lighter gas. Now at a given temperature, the average kinetic energy for the two has to be the same. The kinetic energy only depends on temperature, but kinetic energy is equal to 1/2 mv squared. So if we're talking about the distribution of speeds, if we make the mass smaller, the average speed has to be larger to have the same kinetic energy. So if mass goes down, the average velocity has to go up in order for the kinetic energy to stay the same. So at a given temperature, the kinetic energies of all of them are the same, but the average speeds will be different, because for a lighter gas, you're going to have a higher average speed. This is not drawn quantitatively now, but for helium, the average will shift again to a higher value because it's a lighter gas. As you lower the mass, the velocity has to be larger to have the same kinetic energy. Then finally, if we go to hydrogen, which is the lightest gas in the world, we're going to decrease the mass further, so that means the average speed has to increase again for these to all have the same average kinetic energy. So for hydrogen, it would be a broader distribution, also shifted further to the right. All right, so that's what happens when we change the identity of the gas. There's going to be a sort of inverse relationship between the mass of the gas as its molar mass and the average velocity, because they all have the same kinetic energy if the temperature is the same. But when you change the mass, that's going to change the average speed that you observe, because kinetic energy is a function of both mass and velocity. All right, so any questions on those concepts? All right, so we can start talking about the equations behind this. Now, we're not really going to use these equations to do numerical problems. We're going to see a modified version of this that's more useful for us in the sort of context that we'll see it in. So we're going to use this idea, but not really exactly. But we're just going to introduce it so you can understand the mathematical relationships that we're just sort of talking about. So rigorously speaking, the average kinetic energy, which again can be represented with a bar above it, we said that's proportional to temperature. And what is it related to? So it's going to be 3/2 times R divided by Avogadro's number times the temperature. So again, it's just a series of constants times temperature. So R is the gas constant that we introduced last time. Although when you're talking about speed, there's actually a different value of R that you'll use as in terms of joules, because kinetic energy is going to be measured in joules typically, and we have a value of R that's also in joules. So it's a different value of R, but it's the same constant, just different units. And then Na is Avogadro's number, so we're talking about the average kinetic energy for a single gas molecule. So this is R is per mole, so if we divide by Avogadro's number, that'll give us the average for 1. And then T is the temperature. Okay? But again, we don't need to know the exact equation. We're not going to use this exact equation, but the important part is that it's proportional to temperature. If you increase the temperature, the average kinetic energy will increase linearly with temperature. All right? Now we can also write, as we said last time, the average kinetic energy can also be written as 1/2 times the mass times the average velocity squared, where mass, m is the mass of the particle that we're talking about. All right, so we have two equations for average kinetic energy that we can set equal to each other. So 1/2 average velocity squared is equal to 3/2 r over Avogadro's number times t. So those two can be set equal to each other. And then if we're talking about, and then we can cross multiply both sides by Avogadro's number. So we're just going to cross multiply by Avogadro's number and move that over to the left. Let me write that in a different order. Remember, m here is the mass of the individual atom or molecule we're talking about, and then Na is Avogadro's number. And what we should recognize is that what we can do now is we can solve for the average square of the velocity. So what we're trying to derive here is an equation for the average speed. So we're using basically two equations for kinetic energy that we have, the definition of kinetic energy and the dependence of that on temperature. We're setting those two equal to each other, and we're going to solve for average velocity. Okay? So when we rearrange this equation, what we get is the average v squared average is going to be 3RT divided by Avogadro's number times the mass. And what we should realize from our definition of Avogadro's number and molar mass is that if you have Avogadro's number times the mass of an individual atom or molecule, you have 1 mole of that atom or molecule, so this product is equal to the molar mass or molecular weight of that substance. So we can rewrite this as 3RT over molecular weight. Okay, so we're just changing that term to molecular weight because that's what it's defined as. And again, just to clarify, this average v squared of the bar over it, is the average of the squares of the molecular speed. So we take all the molecular speeds that are present and we square them to get, and then take the average of that. And then if we take the square root of that, we call it VRMS, root mean square. So if we take the square root of both sides of this equation now, we get that the root mean square velocity, which is, for our purposes, you can just think of it as an average velocity, even though it's not rigorously equal to the average. If you have statistics, that'll make more sense to you. But nonetheless, what we get is an equation for the root mean squared velocity, which for our purposes we'll call the average velocity, and that's the square root of 3RT divided by the molar mass. So really the average speed of a gas molecule depends only on two things. It depends on the temperature of the gas and it depends on the molar mass of the gas. And then of course two constants as well, but the only two things that are determining that are the temperature and the molar mass. So that's how we get an equation. Now as I said, we're not going to have homework problems that require us to use this equation in the exact form that it's in, but understanding conceptually these relationships can be helpful for some of the problems we'll have. But just as a demonstration, let's look at, what is the RMS speed, the average or RMS speed for a sample of argon gas at 17 degrees Celsius. So let's just use this equation. Like I said, you're not going to have to use it on the homework, but we can do that quickly. Let's just figure out how fast on average would this be moving. So argon is a pretty common gas that we use in laboratory settings. 17 degrees Celsius is a reasonable temperature, probably similar to what it is outside right now. And VRMS, as we said, is going to just be 3RT divided by the molar mass. All right, and as I said, for these types of calculations, if we were going to do them, we need to use this value of R that's in joules, which is the other one that's given on the periodic table. All right, so we're going to use that value of R. The other one is in liter atmospheres. If you do that, your velocity would be in some weird unit that's not meters per second. If we use this value of R, we'll get a speed in meters per second, and now we just have to plug in the numbers. All right, so 3 times R, which is 8.314, And then the temperature has to be in Kelvin for any of these calculations. So that's going to be 290 Kelvin, because temperature is 17 Celsius. We add 273 to that, so we get 290 Kelvin. And then we're going to divide that by the molar mass of the gas. Now, the other weird thing about this equation, again, we're not going to actually use it in homework questions, so don't forget about it. But the other weird thing is that joules is a compound unit, which I believe is, what is it, kilogram, meters per second squared, or something like that. But anyway, you have to have your masses in kilograms for this to work also. So what we need is the molar mass of the gas in kilograms per mole to be able to put it into this equation. So for argon from the periodic table, it's 39.95 grams per mole, but we have to convert that to kilograms to be able to use it in this equation. As I said, we're going to derive a form of this equation that's sort of in a relative terms, which we're going to actually use, and that one doesn't involve this unit problem, so we can go back to what we're used to in a little bit. But we have to use kilograms if we're going to actually use this equation. So it's going to be 0.03995 in kilograms per mole. That's because joules, which is the energy unit that R is in terms of, is a compound unit that involves kilograms, not grams. All right, but when we put the numbers in and work it out, what we get is 426 meters per second. And that's pretty darn fast. So we should hopefully appreciate when I introduced at the beginning that gas molecules are moving around really fast, in this case atoms, if it's argon, are moving around really fast in constant motion. We can see that even at a reasonably comfortable temperature of 17 Celsius, they're moving on average 426 meters per second. And I think if you're more familiar with miles per hour, I think, what is it? Is it 2 meters per second is 1 mile per hour, or vice versa? I don't remember that exactly. But anyway, this is going to be on the order of hundreds of miles per hour for the average speed of a gas molecule. So it's pretty fast that they're moving around to exert that regular, sort of 1 atmosphere pressure we normally see for gas molecules. They're moving at a good clip. So this just sort of demonstrates numerically what that typical number would be, just in case you were curious. Like I said, we're not going to actually use this equation in homework questions, but you should be familiar with it so you can at least answer conceptual things related to it. All right, so any questions on that? So what we are going to use this relationship for, I guess I duplicated that slide, so I don't need to do that again, sorry. What we are going to use this for is a concept called effusion and diffusion, which is related to how fast the molecules are moving. So this is an actual property of a gas that we're going to talk about, and we're going to primarily talk about it in a relative sense, comparing two gases to each other. How fast does one effuse? How fast does one diffuse? So let's first talk about these two definitions, effusion and diffusion. They look very similar. They mean slightly different things, but mathematically they're the same because they both just are related to how fast the gas molecules are moving. So effusion is escape of a gas through a tiny hole. In other words, it's a leak rate. How fast is it leaking out? So if you have a container of gas and you just punch a small hole in it, the gas will leak out, and how fast it leaks out is called the effusion rate, and how fast that occurs is related to how fast the molecules are moving. So the faster they're moving, the faster they're going to find that hole and leak out. So it's again related to how fast the molecules are moving in that sample. That's called effusion. Diffusion is the movement of a gas through another gas. So it's more about how the gas travels through space, not how it leaks out, but how it actually travels through an area. And so diffusion you could probably appreciate in sort of a everyday life conceptual example. So you guys know, you've probably smelled a gas leak before, hopefully not too often or too intensely, but and the substance that you actually smell when you have a gas leak is not the natural gas itself. Natural gas is odorless, but they add a little tiny bit of a sulfur-containing compound. I think it's probably dimethyl sulfide or something like that, some small molecule sulfur compound, which is has a very strong smell. So that's why they do that, so you can actually smell it yourself and detect a leak, even because with regular natural gas, you would never know that it's leaking until you lit a match and it's too late. So, so they put a little bit of something in there to make sure that you can smell it, so it has a very strong smell. So if I were to have a natural gas leak right here at the front of the room, let's say there's a natural gas line running under my desk here, and it starts leaking, eventually everybody in the room would smell it, right? And that's because those gas molecules are diffusing through the room. They're moving through the gas that's in the room, and they're traveling in all directions. And how fast that diffusion would happen, again, is related to how fast the gas molecules are moving. So the faster they're moving, the faster they'll diffuse, the faster you would smell that. And so both of these concepts, effusion and diffusion, relate to movement of gas molecules, and they're both directly related, of course, to how fast they're moving. So both of these are proportional. The effusion rate or the diffusion rate are proportional to VRMS. The average speed, as we talked about. And so the way we usually sort of compare these two things is going to be not, again, in an absolute sense, but by comparing two gases to each other. How fast does this gas effuse or diffuse relative to this other one? And so we're going to write sort of a ratio of two. So if we have two gases, A and B, the way that we're going to approach these types of problems in this course is always going to be in a relative sense, comparing the rates of those two. And the rates are directly related to their VRMS. Sorry?
What does that say?
Both are proportional to VRMS.
VRMS, okay.
Yeah. And so what we're going to do is we're going to write in VRMS for both of those is 3RT divided by the molar mass. So the molar mass of A for gas A. Same expression for gas B, but with its molar mass instead. So if they're at the same temperature, which is how we would typically compare them, then the ratio of their rates of effusion or diffusion is just the inverse ratio of the square root of their molar mass of B over A. So if we simplify this equation, 3RT divides out because it's the same for both, and then you just have a ratio of molar masses, but they're inverted. And again, that's because the higher the molar mass of the gas, the slower it will be effusing or diffusing, and vice versa. So the rate and molar mass are inversely related as a square root relationship, so that's why rate A over rate B is molar mass of B over molar mass of A. So that's going to be the standard form of this equation in terms of rates of effusion or rates of diffusion. That would be how it comes out. Now there are some variations in this that we need to be familiar with. So the way the problems can be set up can be slightly different. It's the same concept and essentially the same equation, but we'll see there's some slight variations. So the first to realize is that the speed or the rate is going to be distance divided by time. That's the definition of whenever we talk about a rate or a speed, that's what we're referring to. So in some of these Graham's law type of scenarios, so this equation that I just derived is called Graham's law of effusion or diffusion, and they can be set up in different ways. So we can talk about, first of all, in the case of diffusion, how far is the gas traveling? So let's say I take 2 samples of gas and put them here at the front of the room, and over a certain period of time we measure how far they diffuse throughout the room. So that would be in terms of the distance that they're traveling. Well, distance and speed are directly related to each other, so it's going to be the same exact equation we just derived, but just in terms of the distances. So if you're talking about how far a gas diffuses in a certain period of time, the ratio of those two is again going to be given by the same equation, inversely related to the square roots of the molar mass. So this equation is the same as the equation we derive for rates of effusion or diffusion. We're talking about the distance that they travel, which would be more related to diffusion, but nonetheless, if we're talking about the distance that a gas travels in a certain period of time, it's going to be the same equation that we just derived. Now, the one that switches a little bit, though, is if we're talking about, in terms of time, how long does it take for a gas to effuse or diffuse? So if we look at the definition of speed, speed is inversely related to the amount of time. So in other words, a gas that's moving faster or gas that's diffusing or effusing faster is going to take a shorter amount of time to effuse or diffuse. So again, doing the same thing, if we take 2 gas molecules here at the front of the room and let them diffuse to the back of the room, the one that's going to go faster, that's going to get there first, is the one that's going to have the faster speed, which is going to be the one that has the smaller molar mass. So in this case, we have to invert one side of the equation. So if we're talking about the time that it takes gas A to effuse or diffuse relative to the time that it takes gas B, in this case, it's going to be directly related to the molar masses, A over B. So we have to flip the one side of the equation if we're talking about units of time in this context. Again, that's because the gas that has the smaller molar mass is going to take a shorter time to diffuse or effuse. The gas that has a larger molar mass will take a longer time. So in this case, the two are directly related. So you have to remember to do that if you're approaching problems like this, that if we're giving you units of time, you have to make sure you flip one side of the equation, and in that case, the time and the molar masses are directly related to each other. For the other two, distance that they travel or rate that they travel or diffuse, that's going to always be inversely related. So make sure you keep that straight. That's a common source of confusion in this part of the course, but the equations themselves are not very difficult to use. All right, so any questions on that before we get into some example problems? All right, so let's just do a few and see how they're set up. So we have one here, which is we have an equal molar sample of hydrogen and helium. That means you have the same amount of each. And we want to know which gas effuses faster and by how much. Again, effusion is leaking, but both of them use the same equation. So here we're comparing the rate of effusion, which one effuses faster. So we're going to just use that standard form of the equation. The rates of the two. We'll do hydrogen over helium, but you could have set it up either way. You'll get the same outcome either way. So we're going to do hydrogen over helium, and that's going to be equal to the inverse square root of the molar masses. So if we have rate of hydrogen on top, we need to have the molar mass of hydrogen on the bottom on this side of the equation, and then rate of helium on the bottom on the left means that the molar mass of helium goes on the top over there. And so to compare the rates, all we have to do is just look at the square roots of these molar masses. So helium from the periodic table is 4.00 grams per mole. Hydrogen, H2. Remember, hydrogen is H2 gas. The standard state of hydrogen we talked about in chapter 7 is H2. So here we're talking about H2, which has a molar mass of 2.02. That's 2 times the atomic mass of hydrogen. So what that comes out to then is the square root of 1.98, which is 1.41. So the ratio of hydrogen to helium is 1.41, the rate of effusion for those two. And so that means hydrogen is effusing faster than helium by a factor of 1.41. So if this was a multiple choice question, you would choose an answer something like this. Hydrogen effuses 1.41 times. Sorry?
Why is hydrogen the one that's diffusing?
Because we're taking a ratio of the two rates, and that ratio is greater than 1. So whenever a ratio of two rates is greater than 1, the one that's in the numerator is the one that's going to be moving faster.
Yeah.
So whatever those absolute rates are, we don't know, but the ratio of those two is 1.41, with hydrogen being faster because it's in the numerator. So if we had inverted this, if we had done helium over hydrogen, which would have been fine, we would have gotten a number that's smaller than 1, the inverse of this, and in that case we would conclude that helium is moving slower than hydrogen by that factor. So it would give you the same result, just stated slightly differently, okay? But the conclusion here is that H2 effuses 1.41 times faster. All right, so that's one way to use this equation. Just again, relative rates is kind of the sort of default that we have, or the easiest way to do it. Any questions on that one from anyone else? All right, and then the next one deals with, in this time we're talking about units of time. So here we have, if it takes 1.25 minutes for 0.01 mole of helium to effuse, so again, effusing is leaking. So let's say we have a 0.01 mole balloon of helium and we poke a small hole in it without popping it, and it takes 1.25 minutes for it to leak out. How long will it take for the same amount of ethane, C2H6, which has a molar mass of 30.08, it's one of the components in natural gas, although not the major one. How long will it take for that to effuse? So in this case, we're talking about the time that it takes something to effuse. So we're talking about a ratio of 2 effusion times. And again, we can do it either way, with either one on top or bottom. We'll see it's a little bit mathematically simpler to put the time that it takes for C2H6 on the top, because that's what we're trying to solve for here. So it'll be less algebra to solve for this if that's our unknown in the top of this. But again, you can write the ratio in either way, you'll get the same answer. But again, as we talked about before, when we're talking about the amount of time that it takes something to effuse or diffuse, in this case, the equation, we have to flip one side, and the molar masses are now directly related. So if we're writing it in this way with C2H6 on the top and in units of time, the molar mass for C2H6 has to go on the top under the square root as well. All right, so that's, again, the part that people often forget is to flip the equation when we're talking about time that it takes, or here we're talking about it in terms of the amount of minutes that it would take. All right, so what we're going to do is we're going to solve for the amount of time that it takes for C2H6 to effuse. That's our unknown, and we can just start putting the numbers into the equation. So it took 1.25 minutes for the sample of helium to effuse, and then the square roots of the molar masses. For C2H6 is 30.08, and in this case, as we said, we don't need to change, I didn't mention this in the last problem, you don't need to change this to kilograms per mole because it's a ratio of 2 molar masses. So as long as you keep them both in grams per mole, you're fine. So we don't have to change units in this case because we're not using R as part of the calculation. So it's just going to be a ratio of those 2 molar masses, and so then we just cross multiply both sides by 1.25, and so that means the time for C2H6, so we divide, take the square root, and then multiply by 1.25 is going to be 3.43 minutes. All right, so it takes about almost 3 times as long to fuse as the helium. So when you're doing problems like this, it is helpful to, again, think about the concepts that we introduced at the beginning of today and see if your answer makes sense. So ethane is a heavier gas than helium. We can see that directly from the molar masses, that the molar mass for this is 30, this one is 4. Okay, so it's a heavier gas. And we know that heavier gases on average are moving slower at the same temperature, because when you have a sample of gases at same temperatures, kinetic energies are the same, but the one that's heavier has to move slower to have the same kinetic energy. So if ethane is moving slower, it should take longer for it to leak out, and we do in fact see that our answer is longer than the amount of time that it took for the lighter gas. So it is helpful to check that your answer makes sense, because like I said, it's easy to sometimes forget that you have to flip this equation or to flip it when you're not supposed to and so on, but checking that your answer makes intuitive sense can be helpful for these problems, because it's mathematically simple. You have to make sure that you have these written out in the right order to be able to solve it correctly. So it does take longer for C2H6 to effuse, and that makes sense because it's a heavier gas, meaning that it's moving slower if we have the 2 gases at the same temperature. All right, any questions on that? Yep.
How do you know like which gas to put in the diffusion?
So it turns out it doesn't matter. You just have to make sure that however you set it up, you make sure that the other side of the equal sign is set up correctly as well. So we could have written this also in this way. We could have done the time for helium over the time for C2H6. And then in that case, what we would write is we'd write the molar mass for helium on the top and C2H6 on the bottom. Because for time, they're going to be directly related, meaning whatever's on the top over here has to be on the top over there, and vice versa. So you could have started with this, and it would have been fine, would have gotten the answer. This one is algebraically a little bit more complicated because what you're solving for is in the denominator here. So you'd have to basically cross-multiply and then divide by this complex fraction there. So it's not as straightforward algebraically, but it would work out either way. So you'll get the same answer. So it doesn't matter how you start. I start these with the benefit of hindsight, having done the problem before, knowing what's going to be most convenient algebraically, but if you do it the other way, you'll get to the same answer, just with slightly more difficult algebra. All right, anything else? All right, and then I guess, how many more of these we have? More? Yeah, we're going to, all right, yeah, let's do one more, and then we'll talk about a slightly different approach. All right, so here we have, if 7.23 milliliters of an unknown gas effuses in the same amount of time as 13.8 milliliters of argon, what is the molar mass of the unknown gas? And so again, here what we're going to be looking at is the sort of standard form of the equation, the rates of the 2 gases. We can write this ratio in either order. So we have an unknown gas, which I'll call X, and then argon, which has symbol AR. So the rate of argon over the rate of the unknown gas. And so here we're talking about the amounts that are effusing, the amounts that are leaking out, but that's proportional to the rate. The faster the rate of effusion, the more that's going to leak out in a certain period of time. So we're going to use this form of the equation. We're not talking about how much time it takes, we're talking about how much gas is actually leaking out. And that's going to be equal to, again, the inverse square root ratio of the molar masses. Here's going to be X over argon if we write the equation in this way. Or we could have flipped both sides of the equation, and that would be a perfectly fine starting point. Now what we're solving for is the molar mass of the unknown gas. That's what the question is asking for, what's the molar mass? So if you have a fraction under a square root, the other way that you can write it, which is sometimes convenient, especially when you start doing algebra, is just the ratio of the two individual square roots. So we can rewrite this in this form, which for this problem is going to be a little bit convenient just for getting the algebra right. And so this is what we're solving for here. All right, and so we can just start putting the numbers in to solve this equation. So the rate of argon is proportional to the amount that diffuses out. So for argon, it's going to be 13.8 milliliters is how much gas is leaking out in a certain period of time, and that's proportional to the rate that it leaks out. For the other gas, it's 7.23, and that's going to be equal to the square root of the molar mass of X divided by the square root of the molar mass of argon, which is 39.95. Now we haven't done algebra yet that requires us to solve for something that's under a square root, so hopefully you remember how to do that from your math classes, but if not, the way we're going to do this is we're going to square both sides of the equation. That'll get rid of the square roots. And so then what we end up with when we take the square of both sides is 13.8 divided by 7.23 squared, that whole thing squared. And then we cross multiply as well, times, we get rid of the square root sign when we square that side, so we're going to multiply that times the molar mass of argon. That's going to be equal to the molar mass of X. All right, so I'm just working through the algebra a little bit here just to make sure you know how it works. So whenever we have to solve for something that's under a square root, we need to square both sides to get rid of the square root. And so we square this side, square the other side, gets rid of the square root, and then cross multiply and solve for molar mass of X. So what we end up with is the molar mass for this unknown gas X is 146 grams per mole. All right, and again, we should check that our answer makes sense, which at least qualitatively it does, because we see that in the same period of time, less of our unknown gas leaks out. And so if it's leaking slower, if less of it is leaking out over time, that means it should be a heavier gas, it's moving slower. And so we see that our molar mass here is larger. So if we had inverted one side of the equation, we would have gotten a molar mass that's smaller than argon, and that should immediately raise a red flag that our answer is not reasonable, because if it's leaking slower, that means it should be a heavier gas, not a lighter gas. Okay? So any questions on that? So again, these problems here, one equation, two slight variations on the equation, and just one of those things you're going to have to solve for depending on how the problem is set up. Yeah, question over here?
So if we're given rate, is that, or if we're given milliliters, is that going to be the rate all the time?
Yeah, so the amount that diffuses is basically the rate is basically the amount that diffuses over time. So if we're just giving you the amount that diffuses in a specific time, the ratio of those two values is the same as the ratio of the rates. It's the same period of time. So I didn't explicitly cover that, but that would follow the same relationship as the standard form of the equation. Anything else? All right, the next thing we're going to move to, which is related to this, is going to be a common diffusion experiment that we're going to sort of describe. And I think you guys do this in the lab, and it's one of those experiments that never quite works out the way it's supposed to, but in theory it's nice, and we're only doing theoretical stuff here, so it'll always work out for us. So what you're doing is to sort of demonstrate or measure diffusion. It's, I don't know really what the practical purpose of this experiment is other than just a demonstration of this. So what you do is you start with two aqueous solutions that will react with each other. So on one side, the text is kind of small, so I'll write it out. You start with ammonia on one side as an aqueous solution, and then you start with HCl on the other side. And so these are both aqueous solutions. You soak a cotton ball in both solutions, and then you plug the ends of a tube with each cotton ball. So you have ammonia on one side, HCl on the other. And even though these are aqueous solutions, the solutes that are present, ammonia and HCl, are actually gases. So some of them are going to come out of that aqueous solution, and they're going to start diffusing through the glass tube. So what you'll essentially have is ammonia gas diffusing this way, and HCl gas diffusing that way, and they're going to meet somewhere in the middle. Now, when they meet each other, that's when the reaction is going to happen between the two. So this is an acid-base reaction, sort of. Not exactly the type that we talked about, but it is an acid-base reaction. So the ammonia gas is going to diffuse from one side, and the HCl is going to diffuse from the other. And when they get together, they're going to form this ionic compound, ammonium chloride, which is a solid. So what this picture is showing here, both in the cartoon form and here's a photograph of what it looks like, when the two gases meet, you're going to see sort of a white ring of solid that forms where that ammonium chloride has been generated. So that's exactly where they react with each other. And so what you can do is, again, just to sort of spell this out in words, the two reactants start at opposite ends of the tube. The two gases diffuse towards the center until they meet up with each other, and then they react to form the solid ammonium chloride. All right, and then you'll visually see that white ring where they react. So knowing the relative rates of diffusion for the two gases, which we have equations now to describe, we can predict where exactly the two gases are going to meet with each other. Is it going to be exactly in the middle of the tube? Is it going to be closer to one side, closer to the other? We can use Graham's law of diffusion to predict that. All right, so here's how the problem would be set up. Again, there's homework problems like this. I just want to make sure that I do one in class to familiarize yourself with it. All right, so we're doing this exact experiment. We're taking HCl and NH3, releasing them from opposite ends of a glass tube that's 30 centimeters long, so that's exactly 1 foot long. And we want to know how far does the NH3 travel before reacting with the HCl. This is kind of like one of those classic physics problems, right, where if you have a train leaving from Chicago at 60 miles an hour and a train leaving from Cleveland at 55 miles an hour, and they're coming towards each other, where do they meet? This is kind of like that. The two gases are traveling from opposite sides, and they're going to meet somewhere and react with each other, and that's what you're trying to figure out here. So again, sort of a schematic diagram of that. We have a 30 centimeter tube with ammonia traveling in one direction, and HCl traveling in the other direction, and we're trying to figure out where exactly do they meet. So we're looking for this distance here, the distance that ammonia travels before they meet with each other, and then the distance that HCl travels we could also find if we needed to as well. So for this, we're going to have two equations and two unknowns because we don't know the distance for either of these. We're looking for the distance for ammonia, but we don't know yet what the distance is for HCl either, so we have both of those as our sort of unknowns here. But what we can do is we can use Graham's law to write a ratio of the distances. So we said that the distance that they travel is directly proportional to how fast they're moving to their rate of diffusion. So that's going to be equal to the inverse square roots of the molar masses. So if we're taking the ratio that HCl travels over the ratio that NH3 travels, again, we could have done it either way. You'll get the same answer, but this one works out a little bit easier mathematically. It's going to be the inverse square root ratios of their molar masses. So it's going to be NH3 over HCl if we're writing it in this way. And so we gave you the molar masses of both of these gases directly in the problem. So NH3 on top is 17.03. And HCl on the bottom is 36.46. And so that's going to be equal to 0.683. So the ratio of the distances is 0.683. So this distance for HCl divided by NH3 is 0.683. Or alternatively, we can cross multiply and write this as the distance that HCl travels is 0.683 times the distance that NH3 travels. So right away, this tells us that NH3 is traveling a greater distance because the ratio is less than 1, meaning that the larger values in the denominator here. But in terms of what that distance actually is, we need another equation. Well, because the whole length of the tube is 30 centimeters, the distance that they travel to meet each other, the sum of those two has to be equal to 30 centimeters, right? So the whole distance is 30. And so the other equation we're going to write is that the distance that one gas travels plus the distance that the other gas travels has to equal the total length of the tube that they're diffusing through, which is 30 centimeters. So then we can plug this in. So we're solving for the distance that NH3 travels. So we're gonna use this relationship here and replace the HCl distance with that. All right, so we're gonna substitute that into this other equation here. So we get 0.683 times the distance that NH3 travels plus the distance that NH3 travels is equal to 30. And so when we solve for that, the distance that NH3 travels is equal to 17.8 centimeters. So a little bit more than half. All right, so they don't meet exactly in the middle. The NH3, because it's moving faster, is going to travel a little bit further. So when we solve it, this distance is 17.8 centimeters, and this other distance would be whatever the rest is, which is 12.2. I did that right in my head. Okay, and so that's the distance that NH3 travels before it reacts with the NH3. So that's just another way of sort of experimental way of demonstrating diffusion, and we can predict, and then you can do it in the lab and see if your prediction matches up with what you get or not. So any questions on that one? So it just takes it a little bit further by introducing, again, a second relationship that we have to use to find out the absolute distance for one of those two gases. And we could have set up either way. We could have solved for either of those distances. We would have gotten all the same information however we did it. All right, good on that? All right, so the last thing we're going to talk about in this chapter, which is purely conceptual at this point, is going to be, real gases. So everything we've talked about so far is an ideal gas. So an ideal gas is one that obeys the ideal gas equation, PV equals nRT, and it's one that would then follow that kinetic molecular theory, all those things we talked about at the beginning of today's class. Now, the reality is that no gas is actually ideal. There's no such thing as a gas that behaves perfectly ideally. Every gas is going to deviate at some level from this ideal gas behavior. Now, in normal temperatures and pressures that we work with here on planet Earth, for most gases, those deviations are very small, so it doesn't affect the measurements we make or any predictions we would make about those gases. But for certain types of gases and under more extreme conditions, really high pressures or really low temperatures, for example, we might see some deviations occurring. So in an ideal gas, PV equals nRT. So if we divide both sides by nRT, PV divided by nRT should equal 1 for an ideal gas. So if we measure PV divided by nRT for any ideal gas, if it's behaving ideally, that ratio should always be 1, no matter what the pressure, volume, number of moles, and temperature is. So what we're going to do here is we're going to sort of do a qualitative plot of that ratio, PV divided by nRT, as a function of the pressure of the gas, where we'll keep the volume constant and temperature constant, number of moles constant, but let's see how this ratio changes for different gases. Again, this is all sort of qualitative at this point. So as I said, if it was a true ideal gas, that ratio would equal 1 no matter what, so it would follow this horizontal red line here, but the reality is that they don't quite work that way. So for some gases we have positive deviation. So for a really small gas like hydrogen, we're going to get sort of a gradual positive deviation from this line. So that would be something like what hydrogen looks like. But then for most gases that are bigger than hydrogen, what you'll see is that at relatively low pressures on this scale, they're actually going to dip below 1 for a little bit, and then as you go to really high pressures, they sort of cross back up and deviate in a positive sense. So like for nitrogen, it'll look something like this. Where it starts out dipping below the ideal value of 1, and then it sort of deviates from there. And then as you make the gas heavier and heavier, or change the shape of the gas, there's different factors that affect this that we'll talk about a little bit, the deviations can be different. So for example, if we go to CH4, that one would have perhaps a larger deviation. So yeah, we don't need to necessarily memorize all these different trends and which one is which. That's not really the point of this. It's just to show you that different gases can have different types of deviations. So for a larger gas like CO2, the deviation could be larger before it eventually trends back upwards. So what you can see then is that gases, depending on the condition and depending on what gas you're talking about, they can either have a positive deviation from P equals nRT, meaning the ratio of those two is greater than 1, or a negative deviation, meaning the ratio of those two is less than 1. So the purpose for us in this class is going to be to sort of understand why that happens and, a little bit about, which situations the ideal gas behavior is most closely followed. So before we start talking about the deviations from this ideal gas behavior, let's talk about, when do real gases actually behave most ideally? So, the ideal gas equation is followed in which situations? So they're going to be followed most closely at low pressures, because at low pressures, the gas particles are very far apart from each other. So low pressure, or we could also say large volume. Both of those kind of go hand in hand. So when you have a large volume of gas, or the pressure inside of there is really low, however you want to think about that, the gas particles are very far apart from each other. Because in order for ideal gas behavior to be observed, as kinetic molecular theory tells us, those gas molecules should not be interacting with each other at all. And so if you put the gas molecules really far apart in a large volume, that's going to minimize the interactions between each other, which is going to allow them to behave more ideally.
So what's that stand for? Like what's what?
Large volume.
Oh, large.
So when you're talking about this situation, we're talking about low pressure or large volume.
Oh yeah.
Either one of those go hand in hand. So when we're talking about a gas that's at a low pressure or occupies a large volume, in either of those situations, the gas molecules are really far apart from each other, so they don't interact with each other very much at all, and that means the volume of the gas particles themselves is much smaller than the volume of the container they're in. Because the other assumption of kinetic molecular theory is that the volume of the particles is 0. We recognize that that's not true. Atoms and molecules do have some size to them, even though they're very tiny. And so in a situation where you have a large volume or a small pressure and the gas molecules are really far apart, the volume that they're occupying is much bigger than the volume of the particles, and we can then approximate the volume of the particles as being close to 0, like the ideal gas law sort of assumes. All right, so that's a situation when they behave ideally. And in terms of temperature, they're going to behave most ideally when the temperature is high. And that's because the gas particles are moving very fast. At high temperature, we talked about that a lot today. So as you raise the temperature, they move faster and faster, and because they're moving so fast, they have less time to interact with each other. They don't collide with each other as often. They don't have as much time to interact with other gas molecules. Again, for ideal behavior, we want to minimize the interactions of gas molecules with themselves. And so by having a high temperature, you do that because they're just whizzing around so fast that they don't have any time to, greet each other. They just sort of are moving around. All right, so those are the conditions where a real gas, any gas that we have on planet Earth, will behave most ideally, where it'll be closest to that ideal gas equation of PV equals nRT. So when you have low pressure or large volume, meaning that they're spread far apart, and when you're at high temperature, meaning they're moving around really fast. So those are the conditions. And so as we said, though, in every situation, there's going to be some deviation from ideal gas behavior, which we talked about qualitatively here, how it can differ from gas to gas, and it's a function of pressure and so on. So what we have then to account for that is another equation called the van der Waals equation that corrects for this. So this is an equation, again, that we're not going to actually use to do numerical problems with, but we're going to write it out and talk about it so we can understand conceptually why we have this equation and why there are these deviations from the ideal gas behavior that occur in real gases. So the van der Waals equation looks kind of like PV equals nRT, but it has terms that correct the pressure and the volume for their non-ideal behavior. So it's going to be pressure plus n squared A over V squared. We'll talk about what these different terms mean here in a second, but they're all the rest of them are defined the same way of the additional parameters A and B, and then volume minus NB. So B is another new parameter in this equation, equals nRT. So basically, again, we're putting corrections on the pressure and the volume. Now this equation here is not based on any sort of theory. This is exclusively an empirical equation. So this is basically a math trick. If you guys have ever done, mathematical fitting of data, you know that if you add more parameters to your equation, it's going to fit the data better. That's all we're doing here. So the real data that we showed up here does not follow this horizontal line like it should. It always deviates in some sense. And so what we did in the van der Waals equation, not what we did, but what whoever came up with this did, presumably van der Waals himself, what he did was he came up with this equation where he just added more parameters to make it fit better with the behavior of the real gases. All it is a fitting approach to make the data fit the equation a little bit better. So there's no theoretical basis to this. Now that said, even though this wasn't derived from a theory, at the same time, there are meanings to these A and B terms that we have in here. So let's talk about what those are. So what A does here is it adjusts for the interparticle interaction. So A and B are specific to each gas that we have. So it's not a universal constant in this case. It's a constant that's specific to the gas that we're talking about in using this equation for. So every gas is going to have different parameters, A and B, different values for those parameters. But A adjusts for the interparticle interactions. So again, the ideal gas law, kinetic molecular theory, assumes that the particles are not interacting at all with each other, but in reality they are. Now we're going to talk about those interactions in a lot more detail in chapter 9. But basically in any real sample of gas, there's going to be some attraction between the atoms and molecules in that sample. Again, it's very small if you're talking about gas molecules that are spread far apart and at a high temperature, but there's always going to be some attraction between the gas molecules. And so what that attraction does, because the gas molecules are sticking to each other a little bit, they don't collide with the walls of the container as often as they ideally would, and that lowers the pressure. So we're basically adding a term onto the pressure to correct it for the fact that the gas molecules are, that the gas molecules are attracted to each other, and so the pressure is a little bit lower than you would expect it to be under those conditions. And so we're just correcting that with this term here. So A is a numerical parameter specific for each gas, and you multiply by n squared over v squared. Again, that's just a way to make it fit the data best. There's nothing, there's no real concept behind that. And then the other term B here, it adjusts the volume. So that's included with the volume term, and it accounts for the particle volume of the gases. All right, kinetic and molecular theory assumes that the gas particles have no volume. Of course, that's not true, and especially if you have a gas that is a large molecule, or if you have a gas that's at small volume, high pressure, where the gas molecules are forced to be close together to each other, some of the volume in that container is going to be occupied by the gas molecules themselves. Ideal gas law assumes that the entire container is empty volume, but some of that volume will be occupied by the gas molecules themselves, and so this term accounts for that. It basically reduces the volume by a factor to account for the fact that some of the volume in there is taken up by the gas molecules, not just empty space. All right, so a little bit more about A and B before we wrap up today. So these two terms here, A and B, they're called the van der Waals parameters. Again, we're not going to use this equation, but we just want to kind of know what it means and why we have it. These are experimentally determined values. So again, they're not derived based on anything related to the structure or mass or anything about the gas. They're experimentally determined empirical parameters, and they're going to be unique for each gas. So when you're using this equation, it doesn't apply to all gases in exactly the same way. You have to use the correct values for A and B that apply to that specific gas for this equation to work. So the van der Waals parameters for a really small gas like hydrogen would be smaller than for a really large gas like sulfur dioxide, for example. So the size of the gas molecules, in general, the bigger the molecules are, the larger the deviations because of these two factors here, and so bigger molecules tend to have larger van der Waals parameters. They need larger adjustments to PV equals nRT for them to work. All right, so that takes us to the end of chapter 8. So any last questions on this topic before we close it up? Yep. What's the, sorry? So the reason that they behave differently is because of both the different sizes of the molecules that they have, and as well as how strong the interactions are between the molecules. So in chapter 9, we'll talk about how to predict how strong those interactions are, and that causes some of these deviations that we're seeing. But the reason they behave differently is because the different molecules have different interactions with each other in different sizes, and that's what kind of it relates to. But we don't need to know exactly which one is which or anything quantitative about it, just showing that different gases behave differently. Any last questions? All right, so that closes chapter 8, so we'll get into the last chapter starting next week. Getting close to the end.